I should also say that, or I should probably apologize that kinetic theory, this talk will be quite gradient flow focused, and somehow I'm trying to shove in the theory of gradient flows into the Landau equation, which is legitimately coming from kinetic theory, but most of this is going to be on gradient flows. Hopefully, you can learn something. But if at any point things get too confusing, please feel free to interrupt me with questions. So I thought that my first slide would be on pictures to sort of complement these particle collisions that Karsten showed us in the previous talk. So here I have more or less the same formulas of the post-collision velocities, except maybe you remember the parameter nu in Karsten's talk has now become omega. And the picture in my head, so I'm thinking of sort of hard spheres, but in principle, it does not need to look like that, is that two particles in a gas, represented by these circles here, they collide with incoming velocities given by the green arrows, so V and V star. Omega points between their centers, and then after the collision, they are given the red post-collision velocities. And of course, I'm considering here, because of the formulas, the elastic collision cases. So one property is that we have conservation of momentum and energy, and you can check these given the formulas. So this is for the Boltzmann equation, and I haven't talked about the Landau equation, but I will get to that shortly. And yeah, in a slightly different notation, the equation there is the spatially homogeneous Boltzmann equation. So here you recognize the gain and the loss terms in the square brackets, and then the collision kernel with the giant rounded brackets B is, as I said, it's the collision kernel. And here I've chosen to highlight the two arguments. So the first argument is sort of on the relative velocities of the different incoming velocities. And then the second argument, morally, it depends on the angle of the collision, so sort of the geometry of the collision. The physically interesting case is for the collision kernel is given sort of by this example down here. There are many powers floating around, but mainly the thing that causes a lot of difficulty that to impart upon you is that the gamma and the minus s+1 over s-1, those are negative powers, usually in the physically relevant cases. So they generate a lot of singularities.
Sorry, but the omega now is not the one that's same as the slide before, right?
The omega is the same.
Is the connection between the centers of the particles? It should be the direction of the transferred momentum.
Sorry, the direction of the transfer. Yes, so it would be somehow the post collisions. Yeah, you're right. Sorry, thank you for that first thought of that. Okay, now moving a little bit forward towards the actual Landau equation. There's this scaling involved. So in the Boltzmann collision kernel, if I introduce this epsilon, which has nothing to do with the epsilon of Karsten's talk, but if I scale the dependence of the angle of the collision kernel in this way, so clearly I'm concentrating around angles theta that are small. And when I send epsilon to 0, that's known as the grazing collision. So just to draw the picture again, in the elastic collision case, you can think of whatever two velocities I have initially. Let's say you draw a circle with V and V star as points on the surface. The center of mass, so to say, so the halfway point, is conserved along the collisions, because I'm assuming that my collisions are elastic. So in particular, the post-collision velocities will also be vectors that lie on the surface of this circle. And the angle theta is the angle between the sort of the relative pre-collision and post-collision velocities with respect to the center of mass coordinates that I've shown. So yeah, when you concentrate around small angles, i.e. theta near 0 or epsilon going to 0 in the scaling that I discussed before, what you get is the Landau equation, which Landau wrote in 1936, but somehow the earliest reference for it was in 76 by Lifshitz-Peteevsky that I could find. So it's written here, and we've seen this in the earlier workshop. It's this complicated sort of a second order parabolic equation. There are experts in this room who know about this. And what I want to sort of, the perspective I want to give for this is that what I've underbraced should be kind of interpreted as a non-local, non-linear velocity, sort of towards this gradient flow perspective. So yeah, just as a bit of a reminder, the term that I've highlighted in blue there, at least in my head, I think of it as like a singular, but also degenerate elliptic matrix. So the notation I've chosen here is that capital Pi is the projection onto the orthogonal subspace of Z. And yeah, the last thing is what I just said. This matrix is singular when gamma is negative enough, but because pi is a projection, this is also non-negative, but only semi-definite. So there is a degeneracy here. Okay, and then yeah, so that was sort of pictures of particles and how they interact and the grazing collision limit, and sort of just to go over the structure of my talk. In the next few slides, I'll talk about a little bit about what's been done in the literature, as well as this so-called H theorem, which forms the basis of the gradient flow perspective that I want to share with you all. I will also then share the results, and when I talk about the gradient flow perspective, I'll also use sort of the heat equation, because in my head while working on this project, the heat equation was always a very clean toy model for me to consolidate ideas. And then there's a little bit of a discussion on numerics, as I said, and hopefully an outlook for the many remaining problems and projects. Okay, so the Landau equation that Landau wrote, it's a great description for particle interactions in plasmas. And just to give you a bit about the zoology of the parameter gamma, gamma between 0 and 1 corresponds to what's called the hard potential case. And basically a full treatment of this has been done by Deviette and Villani. Morally, if you want to think about it, when gamma is positive, then the singularity of this diffusion disappears. So that's why it's, we know basically everything there is to know about it. Gamma equals 0 is borderline and corresponds to what's called the Maxwellian case. And so Villani studied this intensely, and yeah, this is more or less also quite well studied. Gamma equals -3, which is the physically relevant Coulomb case, does not have the same amount of knowledge around it. There's intense work dedicated to this, as people in this audience are aware of. One thing to point out is, of course, gamma has gone negative, so the equation is quite singular, and it's very hard to deal with this singularity. But somehow the first major result was due to Guo, who gave a well-posedness result in near equilibrium. So i.e. if you have initial data close enough to Maxwellian, then you're pretty good. Okay, so the general uniqueness for weak solutions for gamma equals -3 is not known. But here I want to point out some work done by Fournier and his collaborators, where they have conditional results up to, but not including -3 using stochastic analytic techniques. So the point there is that you can think of the Landau equation. You can write an SDE associated to the Landau equation and then do some sort of coupling argument. And then sort of as an aside, not really what I'm going to be looking at, but we also saw some talks in the workshop about like this whole regularity theory associated with kinetic equations. So yeah, the list of names there, they've been working intensely on trying to reproduce this DeGiorgi-Nash-Moser regularity theory. So going from elliptic to parabolic and then to the kinetic versions of these equations. And then, yeah, many more people have also studied this equation. And it's very technical and difficult, but yeah, there's quite a lot of interest here. So one thing I do want to sort of put in the back of your minds is that this technology, this gradient flow framework that I'm trying to capture here was sort of motivated by the open problem of uniqueness of weak solutions for gamma equals -3. Okay, so now I can start talking intuitively and formally about the gradient flow perspective for the Landau equation that I want to give. So this is motivated sort of from ideas from Erbar and Villani. So in particular, Matthias Erbar discovered the gradient flow structure of the Boltzmann equation with bounded collision kernels morally. And our goal here was to repeat and extend his results. So also use his technology to characterize the Landau equation as a gradient flow, but for more general kernels, not just for Maxwellian kernels. Okay, so the H theorem, which I guess perhaps is very familiar to all of you, but I'll just say it again and I'll try to give it a different sort of spin. So the H theorem morally says that the Boltzmann entropy, so this integral of f log f, is a decreasing function in time along solutions to the Boltzmann equation and the Landau equation. In particular, the equation that's written there says like if you plug in log f as a test function for the Landau equation and then you do a bunch of integration by parts, this is what you would get very formally. So, okay, well, what are you supposed to get from this slide? The point is that the entropy at time t plus a positive quantity is equal to the entropy at the initial time. So i.e. that more or less quantifies the H theorem, but it also says that the entropy at a later time is different than the entropy at the initial time by precisely this time integral of this quantity I've called d sub L, which I will refer to as the entropy dissipation or Landau dissipation, the rest of this talk. And the whole gradient flow perspective is to try and say, look, we know how the Boltzmann entropy decreases along time. Can we use the entropy dissipation as some sort of metric that tells you this is how it decreases? I.e., can we think of this formulation, this identity that is satisfied as a sort of steepest descent of the Boltzmann entropy? So that was a very vague question that I posed, and this whole project was trying to really understand what was meant by that and to try and really capture this sort of steepest descent idea. So, sorry, I'll stay here for a bit. By steepest descent, yeah, I should say that what I mean is I want to find some metric for which the flow of the Landau equation corresponds to the decrease of the Boltzmann entropy in the fastest way possible with respect to this metric d sub L. And so, yes, just to go through the first of the results that I want to share in this preprint with Jose, Matthias, and Laurent is that there is a metric, which I call d sub L, or the Landau metric, and it satisfies nice properties on the space of probability measures with bounded central limits. So it induces a complete topology, it's stronger than the weak topology, and you have various lower semi-continuity properties plus this geodesic space. Okay, and now in connection to the Landau equation, what we have is that I want to think about how gradient flows with respect to this sort of metric correspond to weak solutions of the Landau equation. And if we consider regularized Landau equation, so I will discuss that in more detail a bit later, but for a regularized problem, gradient flow solutions with respect to the Landau metric exist, and they are equivalent to weak solutions of this regularized problem for gamma in the range of -4,0, so including the Coulomb case. Again, I get that that was somewhat very vague, but I will discuss the exact regularization a bit later. So the main thing that also we wanted to talk about was capturing the full Landau equation without the regularization. And there it's a highly conditional result that was very technical. But anyways, the result that we have says the following. If you avoid the Coulomb case, which is already something that we're trying to think about how to improve, then we have equivalence of Milanese H solutions, which you should just think of as normal weak solutions, with respect to gradient flow solutions, subject to the following three conditions. So the first one, or rather I should say the first two, that the entropy is bounded in time and that the dissipation is integrable in time, those are somehow very mild assumptions, and they come almost directly from the theory of from the Milanese theory of H solutions. The third point, which I think hopefully you can see it's in brown because it's very technical. It's the real conditional assumption that is quite nasty to work around. And this assumption is where this shows why we have to avoid gamma equals -3, because the LP requirement is going towards L infinity when gamma is approaching -3. So that's why we were unable to avoid gamma equals -3. Okay, so those are the results, and now shifting gears a bit, I want to talk about the heat equation because, like I said, it was how I use this as a toy model to think about how I should write things for the Landau equation. And in the theory of gradient flows, it's known that the heat equation, so I've written it in this sort of a very weird way. Instead of the Laplacian, I've written it as the divergence of, and then rho times the gradient of the logarithm of rho. Because from that point of view, it's easier to see the heat equation as the 2 Wasserstein gradient flow of the Boltzmann entropy. And the heat equation, as we all know, also satisfies an H theorem, where formally by plugging in log rho as a test function, you get this, this identity here. And the thing in the underbraced term, I might refer to it as the heat dissipation, or perhaps more standardized, I might call it the Fisher information, because that is what it is. Okay, so there is the H theorem for the heat equation, and it's known in the theory of gradient flows, and the people who study that the heat equation can also be thought of as the gradient flow of the Boltzmann entropy with respect to the 2 Wasserstein distance. So I'm trying to basically take that sort of equivalent idea and transfer it over to the Landau equation. So the first step that I want to do is I want to say the 2 Wasserstein distance has this sort of characterization. So the result from Benamou and Brenier in 2000 said that this optimal transportation distance, the 2 Wasserstein distance, can be thought of as a sort of infimum of a certain energy functional. So this integral of m²/f subject to continuity equation constraints. So this was the sort of alternative viewpoint of the 2 Wasserstein metric, which sort of was called dynamic as opposed to the sort of static optimal transportation definition of the Wasserstein distance. Now, so what I said here is that if I'm comparing F0 and F1, which are, let's say F0 is an initial condition and F1 is T equals 1 of the heat semigroup with initial condition F0, then M equals minus F gradient log F is a candidate flux if F0 and F1 are, points along the heat semigroup. And I get this following inequality. I see that the square of the two Wasserstein metric is less than or equal to the time integral of the Fisher information. So this intimately links somehow a property of the heat equation, which is the Fisher information, as well as the metric. And I sort of wanted to ask, can I say the same about the Landau metric? So that was the motivation for the construction of the Landau metric. Can I replace the Fisher information with the Landau dissipation and sort of use that to somewhat construct a metric? And that was precisely what I did. So, but first, there's some nasty notation to introduce. Here, I've just recalled the Fisher information and the Landau dissipation. So a priori, there's no possible, similarities between them. But if I introduce this differential operator, which I call nabla tilde, i.e. you give me a function of v, and nabla tilde of phi returns a function of v and v star, given by v minus v star to the 1 plus gamma over 2 times the projection applied to the gradient of phi at v minus the gradient of phi at v star. Why have I introduced this notation? Well, in that way, the Landau dissipation has this compact form, and sort of at a distance, it looks very similar to the Fisher information. So morally, the FF star is taking the role of the F from the Fisher information, and I've changed whatever differential operator I have acting on the logarithm of F. There's a factor of a 1/2 that is somewhat irrelevant, but if you like, it has to do with the fact that I've gone from the Fisher information being an integral in one variable x, and then the Landau dissipation is an integral over 2 variables. But nevertheless, it's a constant. Okay, so what am I going to do with this differential operator that I've defined? Well, again, just to recap, the Benemuth-Renier dynamic formulation of the two Wasserstein metric is this infimum over some sort of energy functional subject to continuity equation constraints. The way that I define the Landau metric is analogous to this. What I say is I take an infimum of an energy functional here. So instead of m squared over f, I have m squared over ff star. Again, this has to do with sort of the doubling of variables. And now my continuity equation constraint has replaced the usual gradient operator with the nabla tilde operator, or morally the adjoint of it, which I won't define, but just like with the usual continuity equation, this generalized continuity equation constraint should only be thought of in a weak sense. Okay, so yes, and then another sort of sanity check is that if F0 and F1 are sort of, so if you have F1 being the flow of the Landau equation at time 1, subject to F0 being the initial condition, if you're evaluating the Landau metric distance between those 2 points, then a natural candidate for the flux M is this minus FF star nabla tilde log F, which recovers sort of the motivating inequality for the construction.
Sorry, so just a question. So the nabla tilde is graded in the 2 variables, so it has this symmetric.
Yes, this actually confused me for quite a long time. I would say that there's still some confusion around it, but yes, the point is that the nabla tilde is you give it a function of 1 variable, and then it returns a function of 2 variables. So the adjoint has to go the other way if.
So what is the domain of the continuity equation?
The domain of the in what sense? As in, are you asking what it looks like?
So it will be R2D or RD?
No. It's in, well, okay. I can write this stuff. The part associated with the DTF is in RD, but the part associated with the nabla tilde dot of M is somehow in R2D. So okay, if you fix phi, a smooth test function, what I mean by the weak sense or the generalized continuity equation holding in the weak sense is that I multiply that with this and then I integrate by parts. But more specifically, it will look like so the integral in time, integral in RD, dt by f. This is just in RD. But now with the other guy, I have 1/2 a double integral and then nabla tilde phi dot dm. So m is I've confused m as a measure and a density, but m, if you like, it's yeah. So mathcal m for radon measures on R2D, but it lives in No, but thank you for the question. Like I said, this caused me a lot of confusion, and yeah, it was hard to get my head around it when I first started doing this. So continuing on, okay, the first result that I presented many slides ago said that this metric is good, and here I sort of want to informally prove or explain why the metric is good. Like, why did it satisfy some nice properties that I said? So they were completeness, it's stronger than the weak topology, etc., etc. And the point is that we borrowed a lot of technology from the classical book of gradient flows, Ambrosio and Gigli-Savary, as well as this nice paper by Dolbo, Nazaret, Savary, where they also looked at constructing these sort of dynamic distances. Okay, so what is the structure that is making this metric good? The functional to be infimized or minimized in the definition of the Landau metric is this guy here. Now, the point is, it's basically m squared over ff star. That is a jointly convex integrand. So here, somehow you think of ff star as 1 unit. So yeah, because the integrand is jointly convex, then it has nice properties from this sort of a calculus of variations theory when you're infimizing functionals that take on this form. And this was really developed by the paper in Dolbo, Nazaret, Savary, who said that yeah, everything, you get all the nice things that you want. So for example, the first thing that you immediately get from the joint convexity is the lower semi-continuity. Okay, so that was, yeah, if you like, a sketch about why the metric is really nice. And now I want to talk about this regularized PDE that I discussed very vaguely, but now I'll iron out exactly what I mean by it. So, okay. Recall that I want to think of the Landau equation, or the flow of the Landau equation, as the gradient descent of the Boltzmann entropy with respect to my Landau metric. So what we did at first was we considered a regularized version of the Boltzmann entropy given by this H epsilon. So instead of f log f, you replace f with f convolve g epsilon, where g epsilon is a normalized exponential distribution. And we needed it to be exponential for very technical reasons, for certain estimates to hold. So what is the point here? Well, then I can look at the gradient flow, the sort of gradient descent of H epsilon with respect to the Landau metric. And the PDE that you would get, sorry, this is covering a bracket. I have no idea how much clearer that made things. But the point is that the collision term now reads this with the regularization. So I've highlighted in green the new additions to the Landau equation subject to this regularization. So you have a G epsilon basically around the logarithm terms. Okay, and to talk a bit more, yeah, this, because I've only just changed the entropy that I'm taking the gradient descent along, it still inherits quite a lot of properties of a gradient flow. So for example, this PDE still formally conserves mass, momentum, and energy. And there is an associated H theorem, except instead of using log F as a test function, you have to use G epsilon convolved log of F convolved G epsilon. So, okay. Yes, a little on one slide about theory first, and then a bit about some numerics later. The point is that when we look at this problem, this regularized problem, we were able to show that for any fixed epsilon positive, then, so here I've said curve of maximal slope solutions, but just gradient flow solutions are equivalent to weak solutions, and they exist. How is the existence done? The existence is done by using the very classical Jordan-Kindler on Otto variational scheme. So in this minimization problem, I've inserted somehow, I'm trying to minimize H epsilon, and then how does it go again? Yes, I'm minimizing the Landau metric, and then I've got a sort of H epsilon penalization term. So sort of, if you like the, I'm sorry, I won't finish the thought. But yeah, this is the JKO scheme where I've used H epsilon in place of the normal functional, and then I've put in the Landau metric in place of whatever metric you might use here. So anyways, yes, you go through this construction. So minimizers exist, and then here tau is a fixed time step, and you want to send tau to 0. So you need good compactness properties, but somehow those are very standard estimates to obtain, and you can open the book by Ambrosio Gigli subarray, and yeah, almost as a black box apply them. So the equivalence of weak solutions to the regularized problem with these sort of gradient flow solutions, that's highly, highly technical, and I'll discuss that a bit later, but somehow the most important piece of the puzzle that we need is this chain rule, where if you take the time derivative of the regularized entropy, you get sort of, if you were able to, yeah, it's called the chain rule because I've somehow differentiated in the arguments to get the integral of the nabla tilde of the first variation dotted with m. Okay, yeah, so a little bit of a discussion about numerics. The point is that with Jose, Jingwei, and Li, we looked at that regularized Landau equation, and we introduced a particle method there. So the one caveat to that is that in that project, the regularization was actually using Gaussian G epsilon, whereas here I've just told you that we used exponential regularizations, but somehow the form of the equation is still very similar. And anyways, what just to advertise there, why is this why did this work? Well, the regularization that we introduced, it destroys the parabolic nature of it, right? So perhaps going back a few slides, the G epsilon is appearing wherever there's a logarithm. But what that means is that now this collision kernel, or sorry, this collision term makes sense if you substitute F as a combination of Dirac deltas. So that's why this particle method is valid. And what you would end up with is a sort of interacting particle system. This is basically the regularized equation, but just at the level of, shall we say, characteristics. Yeah, the last bit, if you like, it's the velocity if you interpret the Landau equation as a continuity equation with a non-local, nonlinear velocity. And a few results there, sort of heuristically, we obtained a really good sort of convergence results. This was motivated by Jose's work with Katie Craig and Francesco Pasquini. And so there's no proof yet in our case that as epsilon goes to 0, we recover the full Landau equation, but sort of looking against test cases, we got quite high order accuracy. Heuristically, there was almost something like second order accurate. But again, that's sort of numerical experimentation. We didn't write the theorem down. Okay, coming back to the somehow the full equivalence. So now I want to send epsilon to 0, and I told you that I needed something called the chain rule in order to do it. So just to write it out in full, this is what I mean by the chain. If I differentiate the Boltzmann entropy, and informally, I pass the time derivative inside the f log f, and now I use my generalized continuity equation, integrate by parts. This is what I get, or this is what I mean when I'm talking about the chain. Yeah, so in blue, I want the blue equalities here. So another reason why we introduced the epsilon regularization was because we can write the chain rule easier at the epsilon positive level, and then we wanted to send epsilon to 0. So that was a sort of a theory idea. Okay, but what's the problem, or what's the idea to try and send epsilon to 0? Well, if you look at the nabla tilde first variation bits, or sort of the right-hand side of the chain rule, but at the epsilon level, we need uniform estimates using Young's inequality of these two terms on the right-hand side. Okay, so the terms on the right-hand side come from Young's inequality, and there are two things to treat. So morally in red, that's the regularized Landau dissipation at the epsilon positive level, whereas the green guy, there is no epsilon whatsoever, and that was the functional appearing in the Landau metric. So somehow the green guy is, independent of epsilon. We can pass the limit there. The red guy is the villain of our story. Okay, yeah, sorry. So just to tell you a bit about why the chain rule is necessary and why I'm harping on about it on and on. Formally, in a very hand-wavy sense, gradient flow solutions are curves f, which satisfy the equality written here. So this looks very similar to the H theorem that I wrote, except instead of, say, the time integral of the Landau entropy dissipation with a coefficient of 1, I've split it up into a 1/2, and then I've got another contribution from the integral functional of the Landau metric. So just to give a very, very short proof about the equivalence, if you believed in the chain rule, H solutions, or if you like weak solutions, imply curves of maximal slope by saying choose your flux to be minus ff star nabla tilde log f, so that the generalized continuity equation becomes exactly the Landau equation. And then when you plug that into this equality, or with the chain rule, this equality holds, and then that gives you that you are a curve of maximal slope or gradient. For the reverse direction, again, you start from the chain. So the chain rule says that I can differentiate the Boltzmann entropy, and I get, so I've integrated the chain rule in time, but that's the first line of this. And now I'm going to use Young's inequality with a minus sign. So I get, so here I've multiplied and divided by square root of ff star to separate into two terms. So I have the Landau dissipation, and then I have the other sort of action energy functional coming from the Landau metric. And the point is that starting from a gradient flow solution, this inequality is actually an equality. And since I've used Young's inequality here, that means that there's a sort of collinearity condition in the case of equality for Young's or Cauchy-Schwarz inequalities, which tells me that my flux M has to be minus FF star gradient tilde log F, which recovers then the sort of weak solution, H solution. Okay, yes, so back to sort of this red guy. This was the regularized dissipation, and I said that we need good estimates here, and we need to send epsilon to 0. So sorry, how am I doing on time? Am I terrible?
2 minutes.
2 minutes, okay. Okay, so in 2 minutes, let me just say that I've written the regularized dissipation and then the full Landau dissipation down there, and we want to send epsilon to 0. I do not have the patience or the time to go through the intricacies of this. It was very technical, but somehow the G epsilons, they regularize things, but they are also located in very inconvenient places. So it's not really that easy to take the limit. I guess the most important thing I do want to share is sort of this slide, which was an overarching idea that we had, which used the extended dominated convergence theorem. So the idea is the following. If we have some function I call I epsilon v, and it's written as the product of a function A and B convolved with G epsilon, and I wanted to prove that the integral of I epsilon converges to the integral of AB. So obviously the first instinct is to try and find an integrable majorant for I epsilon, but in this case we don't have one. The expression in the previous slide was really nasty, so there was no hope to find a majorant there. The key realization here is that I don't care about integrable majorants. I don't need convergence in L1, I just need that the integral converges. So what I can say is that the integral of I epsilon, there is an equal sign missing. So right where my cursor is, it's equal to the integral of A times B convolved G epsilon, but that is equal to, so I'm using the duality of convolutions, is equal to A convolved with G epsilon times B. So now I don't need to look at majorants for A times B convolved G epsilon. I can look for majorants associated to A convolved G epsilon times B. So that was just one iteration. We had to iterate this a billion times to get what we wanted, but that was sort of the key realization. Yeah, so this was just technical stuff. So now I'll just end with saying, like, what we did was we gave a gradient flow description of the Landau equation motivated by air-Marsh treatment, Boltzmann equation, and we extended the use of we extended the range of the kernels that we can consider. And we've also looked at the theory for the regularized problem, although there's still a gap there. Some things remaining are that we're missing the gamma equals -3 characterization of the Landau equation as a gradient flow. But most importantly, so I said that uniqueness of weak solutions for gamma equals -3 was open. And one of the motivations for this was, can we use the heavy machinery of gradient flow theory to attack that, of which there's been a lot of work in the last couple of decades. The third thing that was open, but now I'm happy to advertise that it was accepted in nonlinear analysis, is that we can recover the grazing collision limit from the gradient flow viewpoints from Boltzmann to Landau. And I'm also giving a talk on that in one of the later workshops, I think. And yeah, finally, another open problem is the convergence of solutions for the epsilon regularized problem. So how close is it quantitatively with respect to epsilon? Is it to the initial? Sorry. Thank you for your time.
So this regularization is also needed for uniqueness, or you can say something about uniqueness directly sort of in the regional gradient flow or projection gradient flow.
That's a good question. We haven't looked at it there. we can say that solutions exist and are unique, but not using gradient flow techniques. So as in, we haven't looked at this sort of like is H epsilon convex with respect to the Landau metric.
But you could imagine like a conditional result, it's like weak strong uniqueness. Assume there is a solution, for example, then that gives you probably a minimizer of your functional, and do you also then have the uniqueness of that solution?
I would have to think about that. I would guess yes, but it's not done.
And about the regularization, in which case do you actually pass to the limit epsilon to 0? I mean, in the last slide, we talked about this convolution and so many convergence, but I didn't remember precisely in which results you did that.
So this was to get the chain. So as in blue, that's the sort of chain rule at epsilon equals 0. That's what we wanted. But what was easier to show was the sort of chain rule at the positive epsilon level first for fixed curves f. And then once we had the chain rule for epsilon positively, then we wanted to send epsilon to 0.
But if I remember correctly, in the theorems, the epsilon was still somehow present. I don't know.
What do you mean about the theorems?
Because you showed the.
So in this one you mean? Or?
And the two slides before. Or one slide after. Yeah, here, exactly. Okay, so you have the existence is not stable under the regularization.
We don't know, yeah. So like I guess what another thing is like, can you do the JKO scheme with the vanilla entropy and the Landau metric? And you absolutely can, but we don't know that that is in any way related to a weak solution.
And that is independent of the gamma.
That is independent of the gamma, yes.
So there should be a bit of a difference if gamma is greater than -2 and gamma is below -2. Somehow, because we know a lot about the models of potentials and very little about what below -2.
Yes.
So your results should be much stronger when you are in the models of potential case, right?
Yes. So somehow the gamma did not really play, or rather, sorry, let me think about how to answer this. The choice of the regularization, the exponential, somehow it doesn't really care at that level what gamma is, whether it's above or less than -2. In fact, gamma equals -2 is somehow critical for why we needed the exponential regularization, because then the exponential regularization completely and luckily cancels out any singularities, and so that's for gamma less than -2, and then for gamma bigger than -2, there was some growth that it stopped. Yeah.
Just a clarification. So your regularization, G epsilon, is that it's different in the theoretical work and also the numerical?
Yes, it was different.
Okay. Can you elaborate that? Maybe I missed that.
So in terms of what estimate changed, it's not here, but so somehow whatever regularization you choose, you would still get this, which we considered, and it was in the theory. However, when for the theoretical results, i.e. the equivalence with the chain rule, we really needed to use something with only an exponential tail, and sorry, a linear tail, in order to get good estimates with respect to certain a priori amounts.
So Maxwellian would be worse.
Maxwellian would be worse here. And it would be worse for the reason that so somehow, yes, okay. If you look at this red guy, That's where the epsilon and regularization come in. With the Maxwellian there, we were able to prove pointwise bounds of this square term. But the point is that with the Maxwellian, that grows like a quartic. And for the Landau equation, I mean, there are a priori estimates, but somehow the most natural ones are conservation of mass, momentum, and energy. So that's only quadratic. Now, if we use the exponential regularization, this square term grows quadratically. So that was why somehow this chain rule was super easy to get at the epsilon positive level for an exponential regularization.
When you say quadratic, you mean that you get higher moments for?
Yes.
Okay.
Okay, so thank you very much. I think. Are there any more questions you're around? And welcome everyone. Okay.